No, wait.
Go ahead.
Hello? No, I think it's working. Okay. Thank you, Laurie, for this kind introduction. Thanks to the Royal Aeronautical Society for the opportunity of giving us from Eurofighter to present our new project. And thanks to the University of the Bundeswehr for hosting this event. This is very much appreciated. And thanks to all the students and to all the people that have come, also colleagues from all times and colleagues that are still working in Airbus Defence and Space and in the other EPCs from Eurofighter as well. So I have the honor here to present what Laurie already said before. This is one of the projects that now will modify the shape of the Eurofighter. My intention is, before I start, first of all, I would like to have a sort of interactive lecture tonight. I'm quite flexible, and I would like to have also inputs, especially from the students, also because we are trying here to target the attention really to the next generations. So students and pilots that we will be flying this new change in the Eurofighter, and students that will become engineers and then will be working in industry. And we need really now good engineers to start developing these changes that you will see in the next slides. Let me check where is the... Yeah, it's here, sorry. So, a couple of words, first of all, related to the Typhoon. I mean, you know that the Typhoon is an aircraft developed by 4 nations in terms of procurement. So we have Germany, we have Italy, we have Spain and the United Kingdom. At the same time, in terms of development, the big 4 industries of these countries have joined together in a consortium that is managed by Eurofighter. And these 4 companies are Airbus Defence and Space Germany, Airbus Defence and Space Spain, BAE Systems, and Leonardo. So we have 4 what we call EPCs, European partner companies, working all together in the development, and 4 nations that we call the core nations. The program started already so many decades ago. And so you will not be surprised in seeing here that the first flight was, let me check if the pointer, that we flew the first time ever on the 27th of March of 1994. And probably 50% of the people in this room were by the time not born even, I guess. I was at the university and I was looking at the Eurofighter as the new project, actually, and I was quite enthusiastic in learning things, but I didn't know that I would have ever worked in this project. That means the project really started many years ago, and since then, the shape has never been changed. We have done a lot of integrations. We have introduced a lot of weaponry. We have introduced a lot of equipment, but the shape of the aircraft has constantly remained the same. It has never been changed. The partner nations started to have their first aircraft in 2003 for Germany, 2004 for Italy, 2003 Spain, and also the United Kingdom. In the course of the years, we have got export nations. So I'm not 100% sure here for Austria, probably this happened earlier, so from 2007, but we have Austria as part of the export nations, the Kingdom Saudi Arabia, Oman, Kuwait, Qatar, and maybe you have heard that this week we have got also a contract from Turkey. The number of aircraft are quite significant. So we have Germany with 181 machines, Italy 120, Spain 118, United Kingdom 159. And also, to be fair, we have in the meantime a so-called Tranche 5 contract from Germany with additional 20 machines. And the mentioned Turkey order that adds to the export nations below, which are Austria 15, Kingdom of Saudi Arabia 72, Oman 12, Kuwait 28, and Qatar 24. I think I can proudly say that this makes this aircraft probably the most successful aircraft in Europe in terms of partnership and numbers. We started, as I said, many years ago, and the evolution of the aircraft, of course, has been focusing mostly the attention on the development of the introduction and the development of new stores. When I say stores, I usually mean weapons, of course, and of new LRIs. But it's now that we are really facing, for the first time ever, the necessity to change something in the shape of the aircraft. But this is not an industry decision. This is something that is driven, of course, by requirements from the nations. And our 4 nations have, as you will see, set up a certain number of requirements that have mandated us to think really deeply how to modify this aircraft to make it even better, which was difficult, in order to be able to comply with these new requirements. Therefore, let me check. So everything starts then from what is the customer requirements. And as you know, we started the Eurofighter journey with a clear message. This has to be the aircraft that is required for air superiority. And of course, this has resulted in an aircraft that requires a very high level of longitudinal static instability. And now maybe it's a good time to break the ice and ask here, so especially to the students, if you have any idea, probably you have, of why static instability is something that is important for an aircraft, for a fighter like the Eurofighter. So please don't be shy. Help me, because I need some support. Any ideas, please? Sorry, say that? Very high maneuverability is a very good answer. Thank you. Any other answer? Any other idea? Please, no, just the new generation, of course. No other ideas. Sorry? Okay, then let's do the following. I would say maybe I stop the presentation just for a second. If I can press ask and let me go. Mark, would you mind? How can I go to another slide? And we go a little bit in understanding what this student said about. So if we go please down, if you don't mind, we go to the backup slides. That one, sorry, this person, this one. Yeah. Thank you, Mark. Okay. So why static instability? So it's a good answer. So for sure, maneuverability, agility could be another one, but there are some others. So let's understand that for an aircraft like the Eurofighter, one of the big requirements that we had at the time was really to be capable of accelerating very fast into the supersonic regime, being able to maneuver, that means a very high level of NZ, so normal load factor, to maneuver in supersonics, and then shoot missiles before being attacked by the enemy. And this is a big requirement, of course. I'm not going to say exactly what is the Mach number. Please, I apologize in advance. It's quite sensitive. And also, I'm not going to say what is exactly the... I'm going to struggle with this. So I think I have to go there. I'm not able to point, apologies. Now, thank you. Mark, that's excellent. Thank you very much. All right, okay. So we are talking about normal load factor of some G's that I'm not going to mention, and flying in supersonic at this high level of factor of normal load factor, which is larger than 1. And so, and the question is, so what is the effect of the instability here? So we have the aircraft here. I just put the Eurofighter, but to be honest, this is absolutely relevant for any aircraft. For any aircraft. So of course, we have the mass of the aircraft acting on the center of gravity with times the normal load factor. Is it working? And we have lift, which is also acting on the aircraft, and we are in supersonics, and therefore the resultant of the aerodynamic force is quite close to the back of the aircraft, is on the rear, which is equilibrating in the vertical axis perfectly the vertical force of the mass times the acceleration. Now, the question that we have now is this aircraft in equilibrium? And the answer is, unfortunately, yes, in the vertical axis, but not in terms of rotation about the center of gravity. And therefore, what do we have to do in this case to achieve the equilibrium? We have to generate a movement of the control surface in order to generate a momentum that is able to counteract the pitching moment coming from the lift, because you can see that the pitching moment coming from the lift is a pitch down moment. And in order to equilibrate this one, we need to generate a force, a downward force, it's okay, a downward force which enables the restoration of the equilibrium of the moment. Now, as you can see, this force is negative. This means it is decremental to lift. And this is quite a point, because it means in order to counteract this decrement, I have to put more lift into the remaining part of the wing, which is the wing without the control surfaces. What is the fact that after some iterations, I will reach, yes, the equilibrium, but the result is that I need more lift into the wing. So the wing has to be bigger in order to generate that lift. Any questions? Good. Then let's ask us now the question, what happens if I move the center of gravity backwards? So you will recognize immediately that when I move the center of gravity backwards, there is a reduction of the lever arm respect to the lift. And therefore, the deflection required for the flaperon, because we call this surface flaperon, is less pronounced. And therefore, this means that we are generating less negative lift. That means that the delta lift that the wing has to generate is smaller. And that means the aircraft will reach again the equilibrium, but requiring less additional lift. That's the trick. The question is now, what happens in subsonics? Because in subsonics, things start to change. So the resultant of the aerodynamic force tends to go slowly to the front. So there will be a point when we reach exactly the center of gravity, for which we will not have any deflection required on the flaperon. And then decelerating further, so this will reach a point in full subsonics when we are quite forward. And then the lift will generate a positive momentum respect to the center of gravity. And now, if we want again to ask ourselves the question, is this aircraft in equilibrium? The answer is again no. I need to deflect the flaperon again, but in this case, I'm generating a positive lift. And this positive lift, of course, is beneficial as long as regards the generation of total lift of the aircraft. So that means I can, as a designer, I can utilize this positive lift of the flaperon in order to reduce the amount of size of the wing. Summary. A shift of the center of gravity backwards, or an equivalent forward shift of the resultant of the aerodynamic forces, is helping in reducing the required lift in both subsonics and supersonics. What's the benefit? The benefit is that then, as a designer, our predecessors, many of them are sitting in this room, they have been requested to design an aircraft with a smaller wing surface area, which in turn, this reduces the mass of the aircraft. And then, if you reduce the mass of the aircraft, because in terms of combat, so you choose an engine in order to reach a certain level of thrust over weight ratio, then you can also allow to install an engine that has less thrust, which in turn reduces again the mass of the aircraft. And then this allows, again, a further reduction of the aircraft size in terms of wing. And this generates a very positive phenomena, which is a reduction of the total mass of the aircraft, further and further in a cycle, until we reach a configuration, which is the one of the Eurofighter, which is extremely small. And in the end, this is all about money. So we are reducing the mass of the aircraft, and the mass of the aircraft is a big contribution to the non-recurring costs of development of an aircraft. So you know that there is a proportionality between the mass of the aircraft and the cost of developing an aircraft, and also a reduction of the recurring costs of the operation of the aircraft. So in the end, the fleets operated by the four nations, so the core nations, are required to invest less money in terms of fuel, in terms of a lot of other parameters that have, of course, quite a good return in terms of taxpayers. Of course, as the student said before, this has a big opportunity, which is the one of using this instability in order to have a very agile aircraft. So very maneuverable, very agile. This is absolutely correct what you said. Okay. And what is the penalty? Unfortunately, the penalty is that we have an unstable aircraft. And an unstable aircraft is something that we have to be a little bit conscious how we handle. Let's try to talk a little bit in terms of stability now. Again, back to the scheme of an aircraft. In this case, is the Eurofighter, but again, it's applicable to any aircraft. The next question is this configuration stable as it is? Stable means that we get a perturbation from an equilibrium condition, and the aircraft, without any input into the control, so we are not changing anything in terms of external forces generated by the aircraft, so we are not moving the surface, is automatically in the condition to go back to the previous equilibrium position. So, of course, you will recognize that this is not the case. The reason being is because as soon as you generate this disturbance in terms of angle of attack increase, automatically you will have an increase in terms of lift. And this increase in terms of lift is not counteracted by anything, and therefore this aircraft will start to increase the angle of attack, and we simply lose the aircraft. Lose the aircraft means simply you start to increase the angle of attack, the loads on the aircraft increase, it gets destroyed in a very rapid time. How do we handle these issues? So, of course, tonight we are not going to talk about flight control systems. It's not the topic, and there are probably many other people with more experience to talk about that. But maybe just to give you a little bit of a hint, it is obvious that the stabilization of such an aircraft is not possible by a human being because of the rapidity how this happens, and therefore you need to have a dedicated flight control system in order to handle the rapid movements that are required in the control surfaces in order to be able to withstand, so to counteract this instability. And by the way, in an aircraft like the Eurofighter, because we are also required to maintain certain levels of safety, I think we can openly say that we need to have a quadruplex system. So we need to have sufficient redundancy because of wrong information coming from the sensors, or simply because some equipment can go and fail. And therefore, there is a required level of redundancy in order to make the aircraft fly. Now, because I just talked about angle of attack, let me simply put the question, how does that work? Just as a principle, just that you have an idea. So you have, again, a variation in terms of angle of attack, a disturbance from the equilibrium point. So what you need to have is to have something that is able to move this surface in a proportional way to the disturbance that you have in order to establish an artificial control to the aircraft. And this is done in a very simple way. This is very simplistic, please allow me that. So you need to measure this angle of attack variation through a so-called air data system, which is an equipment made exactly just to measure the variations of angle of attack. It's not only angle of attack, there are some other parameters, of course, but in this case, just let's remain on the angle of attack. And then through the use of appropriate gains that convert this error in terms of angle of attack into inputs into the control surfaces. So then we inject this discrepancy, and then we command the movement of the, in this case, the flaperon, in order to generate the required counteracting moment. This will bring back the aircraft into the natural previous equilibrium position. Any idea about any other parameter that could be interesting to be controlled in an aircraft beside the angle of attack? Okay. Well, be aware, I have made this very, very simple. In reality, this is a proportional gain. So usually you have a sort of PID controller. So you are then controlling not only the angle of attack, which is the stiffness of the aircraft, but you have also to control the damping. And this is coming from the pitch rate, in this case, in the pitch motion. And then you have to control the error respect to what is the commanded angle of attack. And then you get this through an integrator, okay? But as we said before, this is not a topic for today because we want to go back to AMK, and at the moment we are still talking about the normal aircraft. Let's go now to the topic of the agility or the maneuverability. So why is the agility improved in case you have an unstable aircraft like the Eurofighter? So if you left the aircraft uncontrolled, that means you would not inject any counteracting input in the control surfaces. So you would realize that due to the fact that you have the lift in front of the center of gravity, so just by a disturbance, you would depart the aircraft. So you would increase the angle of attack in an uncontrolled way and very rapidly. So I'm not gonna tell you exactly how many tenths of seconds are required to go from 0 degrees to 80 degrees, but I tell you it's quite fast and definitely not controllable by a human being, okay? So now the question is, why don't we use this intrinsical energy and forces in order to improve the agility? How do we do that? Well, it's simple. The fact is, so if we want to command a certain angle of attack, then what we have to do is just let the lift do the work for us. So because the lift is in front of the center of gravity and we want to pitch up, so we just simply move the elevator. I don't know if you have seen, so we move the flaperon in a way that simply generates a pitching moment a nose-up pitching moment, that then it will simply put the aircraft out of a stable condition, and then the lift will do the work for us. And then you will have a positive mechanical work done by the lift times the distance, the lever arm, times the angle of rotation. And this is work that is coming, let me say, for free. The work then it will be in stopping this one. So this is the maneuver initiation. Then it will go rapidly up, and then the work will be then to control, not to let the aircraft depart. So not to go beyond the value that you wanted to command in terms of angle of attack. Agility, maneuverability. Why is that important? Any hints? Go on. I think it's you again. Exactly. So if you are in the position really to maneuver rapidly, then you have a big advantage in terms of operational use respect to your enemy. So if you are maneuvering and you are able to reach X degrees of angle of attack rapidly in a very short period of time, this will put you in a position to be able to shoot your missiles in a quicker way. It's exactly correct what you're saying. And this is exactly the requirement that we had, well, that my predecessors had at the time of the development of this aircraft. I'm not going to talk about relaxed stability too much tonight, especially for the Eurofighter, just a sec, because anyway, first of all, I think this is you can find this information everywhere on the internet. Just to close the topic, so be aware there have been many studies done in the past. This is one from the NASA on the F-16, and they have demonstrated that just by relaxed stability, you will see here just in the x-axis, the impact of moving the center of gravity backwards. So what kind of improvements you can have in terms, for instance, in terms of required combat fuel, so which is, of course, is reducing. In terms of increase of turn rate, which is quite important in maneuvering, of course. In terms of acceleration as well, because of course you have less induced drag as well, and therefore, for instance, here you have the time for the acceleration from Mach 0.9 to 1.6. So you have a certain number of seconds of reduction, which makes a difference. And last but not least, so also the impacts into the normal load factor, so which is important for the so-called ITR, which is the instantaneous turn rate, which is the turn rate that you can achieve instantaneously. Okay, there are many other advantages. I think I hope I brought you a little bit the background of what have been the constraints and the requirements for the design of this aircraft. I would say 40 years ago. Any questions so far? I think you still look shy. Okay, then let's go back now to the rest of the presentation. I don't know why it's not moving. It's not moving, is it? Now it's. Sure. That's fine. Okay. Smart. Okay, good. So going back, requirements. We were talking about requirements and we got stuck a little bit in the static instability of the aircraft. So, of course, the requirement on static instability has dictated the way this aircraft has been developed in terms of air-to-air superiority. So the result is that today we have a very small aircraft If you compare this against the competition, this is a really small aircraft, but with a very high performance. And what happened in the meantime is that the requirements have started to evolve. So all the, let me say, all the enemies have changed a little bit their attitude, and the enemy has changed a little bit in the last 30 years, definitely. And therefore, we have started to get requirements from the nations that were a little bit different. And this has led to a shift in the focus from the air-to-air role to the air-to-surface role. Now, the way we then achieve fulfillment of these requirements was with the so-called enhancement phases 1 and 2. So the phase 1 and phase 2 dealt with the continued aircraft development to provide a swing role. The swing role is that capability that allows us to be, let me say, good in air-to-air and the air-to-surface role, so the bombing role at the same time. Then we started to integrate new stores, just to mention here the Meteor, the laser designator pod that is required when you have some precision guided munitions, so standoff weapons and so on. So there has been a lot of focus in implementing, introducing air-to-surface integrations into the aircraft. Then there was the phase 3, when we have been requested to increase the weapon flexibility with the data-driven weapon integration. And especially, I think phase 3 concentrated mainly in the introduction of a so-called ISCAN radar into the aircraft, which is the ECRS Mark 0. Then there is this phase 4, and please let me skip it because this is where we are now, and go to the future first, which is the long-term evolution. We have people here beside me that have really defined the long-term evolution of this aircraft. So this is mainly expanding further the capabilities of the avionic architecture. So improving the computing capacity, the high-speed data transmission, and the situational awareness for the pilot. This means that we have new sensors and advanced weapons, and this is what it will be the further improvement of the Eurofighter in terms of strike and counter-air roles. Let's go now to the phase 4, which is where we are now, and which AMK is part of. And this is a big program that started, first of all, with further introduction of the ISCAN radar. So we have gone now to other radars that I cannot mention here, but there are some other variants of the ISCAN radar. And then the nations started to bombard us, and let me use really this bombarding word, with a number of integration requirements for new weapons, new stores, all at the same time, in order to maximize their air-to-surface role, the air-to-surface role of the Eurofighter. As you can imagine, an aircraft now, as we said at the beginning, that has been designed especially for the air-to-air role and therefore is so small, when you start to put a lot of weapons, massive weapons, new weapons that require and have a lot of interferences, as you will see with the aerodynamics of the aircraft, you can imagine that this is posing actually quite a big challenge in terms of design. Specifically, for this phase 4, we have been requested to integrate a new air-to-surface weapons. We have been requested to increase the mixture of the different type of air-to-surface weapons. We have been requested to do something in order to improve the already good capability of the aircraft in terms of air-to-surface supersonic carriage. We have been requested to reduce, and this is quite key actually, to reduce the time of the integration of any new capability. This is quite key, I would say, because one of the requirements that we have received now is to be quick. And when you have a complex aircraft, in terms of aerodynamics, to react quickly is not that easy. And last but not least, we have been requested to improve the aircraft performance and maneuverability, especially in the air-to-surface role. I would concentrate now in two key topics that are related to the impact of new weapon integrations in terms of mass and in terms of aerodynamics. You will understand anyway that in order to cope with all of these requirements, the current platform, as it was, needed to go through further improvements. It was already quite a good aircraft, and the question was, how can we make it even better? The answer was, we needed really to think about some redesign of the external lines of the aircraft. Yes. And you will see now. So,
it's a bit of a hype head, but he can't operate the bloody PowerPoint.
I think, is it muted? Okay. All right. Let me carry on. Let's try. I take the occasion to have a sip of water. Okay. That was an Ukrainian, by the way. Okay. Thanks, Mark. Let's see if it works. Okay, so we have talked about an aircraft that is very unstable, and therefore you will recognize that when we are hanging stores under these many stations that we have 13 stations. So you will understand that the control of the center of gravity is, of course, mandatory. So we need to understand where the center of gravity is, what is he doing. So in the current Eurofighter, we have already predefined sequences in terms of let's see. So we have predefined sequences for the stores that we carry in which we can release them. So there is a certain order because, of course, you will understand that we need to maintain control of the center of gravity, and therefore we need to ensure that to control the maximum aft CG position, because we said that if the center of gravity goes up, that this is more unstable. And we need to control also the maximum lateral center of gravity, and we need to control the control. This is no, don't know now what it. Now it's good. Sorry, apologies. So you will see this is an example of what it would be the maximum center of gravity in terms of max aft center of gravity position and the maximum lateral CG position. So we said before, max aft CG is important for the pitch stability, of course, and the most lateral center of gravity is important for asymmetries, of course, both from a mass perspective, but also from an aerodynamic perspective. So you would be flying with a very large asymmetries, especially when we are talking about low speed, and therefore we need to balance all of these asymmetries. Now, to further adapt the operational carriage and usage of the new requirements, so mixed air-to-surface weapons, the firing and the release sequence of these aircraft have to be adapted in order to allow, fundamentally, to be completely free of release the mixed weapons as the pilot wishes for operational needs, as you can understand. Now, let's go a little bit in detail. What is the meaning of that? So you see this diagram here is showing you the center of gravity in terms of percent respect to the mean aerodynamic chord. Okay? And in the y-axis, we have the mass of the aircraft. So if you look at, please, at these black lines here, These black lines are defining an envelope which defines all the possible coordinates of the center of gravity and the mass of the aircraft. Okay. In terms of max unstable position, you will recognize that the maximum, so the black line on the back is the one defining the maximum instability of the aircraft from a mass perspective, so static instability. Okay. The most forward is also quite important, both for a maneuverability point of view and also from a controllability point of view, because if you design the alpha gain that I showed before for the max staff CG position, because the gain is going to be the same also for the most forward position, then you could go from an instability of the aircraft to an instability of the controller. So there is a range, therefore, this range, the distance between the maximum forward and maximum aft, is really something that defines the boundaries where the flight control laws have to move. Okay? Now, implementing or introducing all of these new weapons of the P4E and the requirement for fully mixed weapons, so of course, we need to extend the width of these boundaries, and we go from what is the black line to what is the red line. And of course, we are not saying what is the number, because this is unclassified. This is classified, but not being so. Let me say, so it is obvious that what we want to maintain here, what we want to control, is a momentum. So the extension of the CG boundaries is parallel, is equivalent to an extension of a momentum. Okay. Now, momentum of the lift force around the center of gravity is very easy. So is, of course, the amount of center of gravity variation, so this delta here, times the mean aerodynamic chord, times the normal watt factor of what you want to fly this aircraft, mass, and gravity acceleration. So now, I think you can find in Wikipedia all the numbers. I'm not going to give you the numbers, but just to have an order of, let me say, a flavor about it. So we are talking here about tenths of kilonewtons meter. Is this a big number? It is a big number. So if you compare this with the torque, we are talking about momentum, so with equivalence is an engine, as we were discussing today. An engine of a good car, not a Formula One, but a good car, I would say a serious car, so is about 400, 500 newtons meter. And here we are talking about tens of kilonewton meter. So we are talking about two different beasts. So it's a huge moment that needs to be handled by the aircraft in order to be able to cope with all of these new requirements. Topic number 2 is aerodynamics. So this is, of course, again, is not peculiar to the Eurofighter. Again, it's peculiar to any aircraft that is flying, especially in terms of a delta wing. You will recognize that if you have a nice aerodynamic flow on the aircraft like we have on the current Eurofighter, this is going to be penalized by many physical aspects. One is for sure if you are flying in the transonic regime because of compressibility, so the Mach effects. Another one is if you are at extremely high angle of attack. So of course you will start to see some separation. So this is normal. High angle level of side slip, for instance, so side wind. And last but not least, of course, so what is the effect when you have a lot of stores hanging from your wing? They will start, of course, to interact with the main flow field over the wing, and unfortunately, they are not going to make it any better. They are going to just worsen it. So the result is that in certain flight conditions and in presence of large air-to-surface store, or let me say high volume air-to-surface stores, the aircraft can be, the flow field can become aerodynamically unstable. And this is especially visible in the lateral directional axis, which is an axis that we didn't want to make it unstable, because we wanted to be unstable from a mass perspective in the longitudinal axis. But the lateral instability is something really weird. We don't want to go there because it's very difficult to control. So the requirement is actually to be statically stable in the lateral axis. Let's see from an aerodynamic point of view what this could look like. And this is a schematic just to simplify a little bit the concept. I may use the model now. So in this picture, you have an aircraft seen from above with the flying in a certain region of the envelope, could be transonic, for instance, with wind coming from the port side. And what you see is that in this picture, so you have, this is a representation of computational fluid dynamics. So just to give you a flavor, so blue color means suction, so it's negative pressure. Yellow or red color means positive pressure, okay? So what you can see that is that the reaction of this aircraft with this side slip coming from the left is that you have a deterioration of the flow conditions on the port wing, whilst maintaining the starboard wing in a very good situation. So it's still, there's still suction here. So, and on top, you also see that there is this bubble here, and this is a bubble with the reversed flow. This means that there has been a separation of the flow, and you have even negative flow coming over the wing. So really with negative speed. So what's the result of that? Is that the aircraft will react with this side slip coming from the port. It will react with a moment which is negative. So the aircraft will react with this wing, with the starboard wing going up and the port wing going down, which is a moment which is unstable, because for the stability in the roll axis, so the CL beta, so the rolling moment due to the side slip, has to be smaller than 0. That means that the aircraft is unstable, and this condition would be unbearable. So we should need to avoid that condition if it happened. Okay? Now, furthermore, what you see on top is because of this reverse flow, so you also see that even if you wanted to control artificially and to compensate this phenomenon, so you wouldn't be in the position to do that, because your control surfaces that are here and here are almost ineffective, because you don't have control power. This is visible, for instance, here in this sketching here that we have, where you see for different positions of the control surface, again, is the flaperon at the end, the one I showed at the beginning, the presentation. So for when you increase the amount of flap, you expect always to have an increase of the control power. But unfortunately, for certain specific combinations of angle of attack, the effect that you have is that you would even reduce the control power. So this would have a decremental effect into the stability. So that means you have reached a situation where you are unstable, incapable to fly, and on top, you cannot even control it with a controller, with a flight control system. So it's quite a peculiar situation. Now, a little bit of background, and then an explanation of what our engineers in the past 15, 18 years have done, especially the colleagues of aerodynamics in Airbus Defence and Space. So again, this is a sketch which is applicable to any aircraft. It doesn't have to be Eurofighter, it's general literature. So for an aircraft with a delta wing and with a foreplane, of course, so you have that the lift is generated by vortices. And then you have the first vortex. This is the foreplane vortex, this one. Second vortex is the fuselage strike vortex. The fuselage strike, for your information, is that little bit here, the pilot step. I don't know. Don't step on it, please. Then there is the wing apex vortex, which is this one here, very small, but peculiar. And then you have the leading edge vortex. And the leading edge vortex is the responsible of the lift that the delta wing is really creating. Now, the problem of the leading edge vortex is that this is the main lift generator, but at the same time, especially when there are stores that are interfering with it, so it's quite sensitive and therefore is quite influenced. And therefore, there is a certain tendency to be, let me say, that the efficiency of this vortex is somehow can be reduced. This is the bad news. But the good news is that our engineers, by making a lot of tests, especially at the beginning in computational flight dynamics, they have discovered by observation, trial and error, that this vortex is very, very sensitive also to another vortex, which is the leading edge vortex here. And therefore, you can imagine how they came to the idea to try to influence the leading edge vortex by a specific design of the wing that influenced the apex strike vortex. And this is exactly what they did. So through an optimization of the design of the wing apex, and at the same time also through optimization of the fuselage strakes, they have been able to influence the flow stability of the leading edge vortex, which has improved the lateral directional stability and therefore also removed the main cause of the lack of the reduced control power for the flappers. So you see that they have been able to go from a situation which is this one with a lack of suction in the port wing for a beta coming from the port side into a situation where they have completely restored the suction on the wing, so making it very, very similar to the starboard wing, which then restores completely the moment, which now becomes a positive moment, so going out of the side slip, so reducing the side slip and transforming it into angle of attack, which is what it should do in terms of a negative CL beta. This is also visible in this representation, for instance, coming from wind tunnel. Here you see in terms of angle of attack, you see the CL moment generated for negative and positive betas. So if you have an influence of stores that deteriorates the stability, as you can see here, at a certain angle of attack, then through this AMK modification, then you are able to restore it completely. You don't see the collapse anymore. Actually, the CL that you can generate remains quite good, not showing the collapse. What are the changes that then we have put? So we have, first of all, introduced this apex strike, the fuselage strike. And then, of course, because we have been requested also to increase the variety of stores that we are integrating, again, we are going from an air-to-air fighter into a bomber. So then we have increased also the size of the control surfaces in order to generate more pitching and roll momentum in order to counteract, especially the effects that you have in carefree handling, so very dynamic maneuvering, or takeoff and landing with high levels of crosswind. These are the modifications that we are putting now into the Eurofighter. So we are removing the flaps, we are removing the current fuselage strake, and we are putting the extended flaperons, and I will run it again. No, of course. Let's see. Here you. You will remember me for my capabilities with AIT tonight. Okay, here you go. So you can see that we have removed the old components and we are putting the new components into the aircraft, especially the major being the apex strake, the fuselage strake, and as I said, the extended flaps. So now, what is the AMK overview? As I said before, so we have three big components. So these are the leading edge extension root, we have the delta fuselage strake, and we have the extended flaps. What we need also to change is because we are changing the aerodynamics of the aircraft, so we cannot simply put this hardware into the aircraft and let it fly. It would be too easy. So we need to develop a new set of control laws that are able to cope with these new aerodynamics, and even to adapt the avionics software that is on the aircraft. In reality, so the process of the development is quite big. So it starts from gathering data in wind tunnel, a lot of data in different flying conditions, so for different controls, for different Mach numbers, for different angles of attack, and then building what we call an aerodynamic data set. With this aerodynamic data set, which is at this moment still wind tunnel based, then we develop the flight control laws. And when we have the flight control laws, then we start what is called the clearance process. And the clearance process involves all the disciplines from the entire weapon system, so from aerodynamics, flight mechanics, LOADs, and all the other required disciplines. So to give what we call a clearance, so a clearance for flight test in this case. Then we go into flight test, and the first target of this flight test is really to prove whether the data that we have got in wind tunnel is correct or not. And this is the exercise of the so-called aerodynamic data gathering. We do this aerodynamic data gathering. Usually, we will find some differences because a wind tunnel is just a model. It's not the reality. The flight test is the reality, and therefore we will get this new data. And then with this new data, we will update the aerodynamic data set. And with this new update of the aerodynamic dataset, there will be need to adapt also the flight control laws to the final standard, that then it gets cleared finally, and then it gets delivered to our customers. To finish on what is AMK, so we have, so this is a kit that is retrofittable. This means it can be installed in new aircraft, but also it can happily be installed in existing aircraft, and it can even be, because it's so simple, in reality, it's just some hardware and a couple of CD-ROMs, so it can be done even at the air bases, and this is already quite a big benefit also for the customer that decides to retrofit at a later stage. For the aircraft, so AMK is an enabler for the faster and cheaper integration of current and future stores with no compromises in terms of flight performance or in terms of agility, maneuverability, survivability to threats. Not only stores, to be honest, we are also paving the way to integrate some other stores in terms of, for instance, of extended range tanks or some flare and chaff dispenser, so many other items that need to be integrated into the aircraft that would modify the external shape of the aircraft. As I said before, of course, it improves the carriage and the release of the mixed stores and gives some flexible store release flexibility. And just to give you a flavor on that, so with AMK, at this stage, we are able to triplicate the current variety of store mixes that we have today. This is a big number. Last but not least, of course, the AMK is also paving the way to any performance improvement that we may want to put if required. So better point in aircraft capabilities, improved fight. And let me also mention another big benefit. This is maybe not for the customer at this stage, but is for industry, but then it will be for the customer again. So the AMK is bringing again the 4 Eurofighter partner companies that have been working for the last 30 years in integration of avionic equipments, is bringing them back into improvements in terms of the basic aircraft development. So we are talking about basic shape. So this is really the first part of the development of an aircraft. And this is something that is quite key, especially now when we are transferring our attention into the new projects like FCAS or GCAP. So of course, we need to have a certain number of engineers in the company that are able to improve the knowledge of the company in those areas that have been somehow neglected in the last 30 years. And then when this capability is acquired in industry, there will be the engineers that then will develop the next future aircraft projects. And I have to say, by experience, the Eurofighter is a project where collaboration is our strength and is different from other projects going in Europe. So definitely we can be proud of the fact that the collaboration is one of the benefits for the project. Any questions so far? Then I would go to a summary now. So we are back at the drawing board with the Eurofighter. So we are modifying really the external lines. This is a big change. And we are enabling a certain number of capabilities. These go into the department of speed of integration, for instance, go into the department of reach and persistence because we are enabling also increased range, payload, performance by meeting the new requirements of the core nations at this P4E enhanced package, which are related to air-to-surface supersonic improvements, extended range, further mix of stores, carriage and firing flexibility, further enhanced agility and maneuverability, and I would say that's it. And as you can recognize now, talking to the students especially, so we are looking for highly motivated engineers in the future to be part of this journey. We will need people in the next future. The Eurofighter is a project that is still alive. Despite being a very good aircraft in the air-to-air role, we need to further invest into the air-to-surface roles. The nations have committed to contract now. We are really already developing this aircraft, so we have got a big contract from the nations, from NETMA, and we are working on it. And this will be work for the next years. In name of Eurofighter, I thank you very much. I hope you have enjoyed and something as, I don't know, is good for maintaining, let me say, the motivation for the studies. Thank you very much again to the Royal Aeronautical Society for giving us this opportunity. Thanks to the University of Bundeswehr. And again, if you have any other questions, you have been very shy though. Please.
Yes, can I make a question? Can you hear me?
Yes. Yes. But they will not worsen it in, let me say, in a tangible way. So, of course, we know that from an RCS perspective, this aircraft has a certain RCS imprint, is obvious. So, but these changes are not going to modify by much what is the RCS signature.
And my experience tells me this is the first time that an external change to the aircraft contours is taking place. I don't recollect anything having taken place on the Tornado either. To what extent are the facilities with the customers having to be improved and extended to enable these markets to be installed with the customer?
It's a good question. Sorry.
Supposed to be only being installed like it's like
Please repeat the question. You speak the question and repeat the question for the online members.
Okay, so I understand the question is so how these hardware changes are going to be impacting the ability of the nations to install them into their aircraft with their own facilities. Yes, yes. To be honest, so it's a good question because it's one of the requirements, internal industry requirements that we had. It was really the retrofitability of these items. So as long as regards the flaps, this is a simple substitution of a flap that can be done now at the customer facilities. It's nothing really big. It's something that is done in a certain number of time, and I'm not going to say how much time, but it's very, very quick. Okay. Yeah, and there is no machining. Related to the fuselage antenna, this is an LRI. So the fuselage strake is actually an LRI because there is an antenna into it. So it's an equipment that you remove from the aircraft and you put it again. And related to the apex strike, this is there is a solution that is now put. That is, of course, so we will need to drill some holes into the aircraft. This is true, but it's something which is not that intrusive, and therefore the logic is that the customer is going to be in the position to modify in a reasonable amount of time the aircraft and install the 4 components. And then, as I said before, you need, of course, to have a new software for both avionics, FCS, and there is also the utility control system that needs to be updated. So, but these are just CDs that go into the aircraft. This is a question that I cannot answer. Any other question? Yes, please. It's also a good question. So our understanding is, of course, the nations that want to put AMK, they want to have a business case for it. And of course, you will recognize that the old Tranche 1 aircraft are quite worn out in terms of life, and therefore the investment will not pay off. And therefore, the design at the moment is concentrated on Tranche 2 onwards. In theory, it could also be applicable for Tranche 1 aircraft, but these are already not going to fly that longer anymore. And therefore, they are going to be scrapped anyway by the nations. Please. We cannot say for sure. So in terms of age, yeah, definitely no. Age is not going to be changed. Of course, you have to recognize that the AMK goes also in conjunction with new store requirements that need to be integrated into the aircraft. And yes, for those stores, there will be requirements for new age. Yes, but it's not related to the AMK itself. So for AMK, you can install it without requiring any new age. Please. I think I haven't given many attention into this presentation to this topic. Probably I should have. It is true. One of the big requirements is really to be quicker. So now what we are trying to do is the following. So when you integrate a store into, or at least the typical way we integrated stores into the Eurofighter was the one of looking store by store and integrating them. The reason being is because we started with this aircraft was, let me say, was an air-to-air aircraft, and therefore, so at the beginning, the air-to-surface role was not foreseen to come. And then when the first store integration came, what it was done is just to integrate one store. So that means going to the wind tunnel, test that store, check what was the impact, generate the data sets and so on, and do the development. Then it came the second store, and we did the same. We repeated the exercise. And every time we repeated this exercise. And generally speaking, because of the high level of instability of the aircraft, for, let me say, for many stores, you need to develop a certain set of control laws that are dedicated to those stores. Now, having now an aircraft that improves the stability, so this gives you a little bit more room to start to combine stores together. And therefore, we are not implementing a single store anymore, but we are implementing now what we call families of stores. So in the development now, what we are doing is also looking to the future. So there will be certain things that we call a store group. So it's a family of stores that will be integrated now into the design of AMK, which will allow in the future, if a nation requires to integrate a new store XYZ, and this store XYZ belongs to the family that we have already integrated, then from an air vehicle perspective, we will have done a lot of work already. Therefore, the Delta work, it will be just to fly it for avionics and deliver it to the customer. That's the key reason why we are now enabling a big reduction in the timescales required to integrate new stores, because we are doing all of this work upfront now. It will take us a little longer, maybe, but we are trying to integrate families. Okay. Apologies, Eurojet. Yeah. Yes. It is a very good question. Thank you. And it's not the first time we talk about trust vectoring. I think, to be honest, I think what we are doing is the following. With this project, we are paving the way to be able, for instance, to introduce trust vectoring in an easier way, in a less intrusive way. But so technically speaking, we are given the possibility to do so. If there is a customer that has got this interest, this can be discussed. Yeah. Sorry. Sorry, can you repeat the question? Yes. Well, to be honest, I simplified a lot that picture. You're absolutely right. In reality, so when we control the aircraft, we are not only using the flaperon, so we are also using the foreplane. Now, the foreplane has a big, let me say, a big impact on what is the airflow over the wing. And therefore, usually the foreplane is moving at low frequency in order to give, let me say, an optimized flow field over the wing. But then for stabilization, which is high frequency, of course, we are also using the foreplane in order to generate moments because it's capable of generating very large moments. For the simplification of the picture, I didn't put that there, just not to confuse people, but you're absolutely right. You will see in videos of maneuvering that the foreplane is moving quite quickly. Yes. Sorry. You're talking about turnaround of the development of AMK. Unfortunately, I cannot answer this question. No, we cannot talk about this. I'm sorry for that. Any other question?
Questions for the online community, Mauro? One here that says the mod to the LERX seems to go over the Canon exist. Will the LERX influence the ability?
It's a very good question. It's really a good question. Yes, of course there is. So the leading gauge. So sorry, the question is the modification of the leading gauge seems to go over the Canon exist. Will the LERX influence the ability to use the Canon in gun fights or close air support? So of course there is let me say a clash of positions between the gun and the LERX. But we are designing a so-called gun blister in order to allow the firing of the cannon without any impacts. So we don't want the LERX to influence the trajectory of the bullets, and at the same time we don't want the firing of the cannon to destroy the leading gauge route. So it's taken into account. Yes, the cannon remains on the starboard side. Yes, this doesn't change. Well, I would talk forever about this project, but okay. I think it depends on the audience.
We'll do one more question from the online community.
If not, then
we have a question from Anthony Osborne. It says, in case of online questions are answered, what work on AMK has already been done? Is this already largely developed? How much more work is needed?
Yeah. So I would say, so the question is so how much work has been done in terms of AMK and whether it is already largely developed and how much work is required to have it ready for P4E. And if this can also be applied to the two-seat version. So the second one is easy. So of course it can be applied to the two-seat version. If there was a requirement, we would implement it. Related to how much work has been done, so this started many years ago in terms of a research and development project. To be honest, the focus was a little bit different from what is today. So now AMK has completely another focus, which is the air-to-surface part. And a lot of work has been done in terms of demonstrating that the concept works. So all the slides that you have seen in terms of mass distribution and in terms of aerodynamic impact, so this is a concept that has been demonstrated, fully demonstrated in flight. There have been flights in the past in 2007 and in 2016 that have demonstrated the concept. Of course, now we have to go into the development. So that means really to make it work on the aircraft. Therefore, there is a certain time required to go into the complete development and qualification. I don't see any other questions now. Yeah. Okay.
If not, then now thank you very much for the very interesting presentation. And the next colloquium will be in 2 weeks with General Neumann, Inspector der Luftwaffe. I think also students will be there. And Royal Aeronautical Engineering next. Our next their next presentation. It's in
November 9th.
November 19th is the next event. It's in Garching, or?
Yeah.
Yeah, it's in Garching, Munich Aerospace, I think, or? That's up. So, thank you very much. Dankeschön, dass alle da waren. Und wünsche allen dann noch einen schönen Abend und nochmal ganz, ganz herzlichen Dank für den wirklich sehr interessanten Vortrag.
Vielen Dank Ihnen und vielen Dank an die Jugend. Danke.